Muscle contraction is the activation of tension-generating sites within muscle fibers. In physiology, muscle contraction does not mean muscle shortening because muscle tension can be produced without changes in muscle length, such as holding a heavy book or a dumbbell at the same position. Muscle contractions can be described based on two variables: length and tension. A muscle contraction is described as isometric if the muscle tension changes but the muscle length remains the same. In contrast, a muscle contraction is isotonic if muscle length changes but the muscle tension remains the same. Furthermore, if the muscle length shortens, the contraction is concentric. But if the muscle length lengthens, then the contraction is eccentric. In natural movements that underlie locomotor activity, muscle contractions are multifaceted as they are able to produce changes in length in tension in a time-varying manner. Thus, length and tension are unlikely to remain the same in muscles that contract during locomotor activity. In vertebrates, skeletal muscle contractions are neurogenic as they require synaptic input from motor neurons to produce muscle contractions. A single motor neuron is able to innervate multiple muscle fibers, thereby causing the fibers to contract at the same time. Once innervated, the protein filaments within each skeletal muscle fiber slide past each other to produce a contraction, which is explained by the sliding filament theory. The contractions that is produced can be described as a twitch, summation, or tetanus, depending on the frequency of action potentials. In skeletal muscles, muscle tension is at its greatest when the muscle is stretched to an intermediate length as described by the length-tension relationship. Smooth and cardiac muscle contractions are myogenic and can be modulated by the autonomic nervous system. The mechanisms of contraction in these muscle tissues are similar to skeletal muscle tissues. Types. Muscle contractions can be described based on two variables: force and length. Force itself can be differentiated as either tension or load. Muscle tension is the force exerted by the muscle on an object, whereas a load is the force exerted by an object on the muscle. When muscle tension changes without any corresponding changes in muscle length, the muscle contraction is described as isometric. If the muscle length changes while muscle tension remains the same, then the muscle contraction is isotonic. Furthermore, if the muscle length shortens, the contraction is concentric. But if the muscle length lengthens, then the contraction is eccentric. In natural movements that underlie locomotor activity, muscle contractions are multifaceted as they are able to produce changes in length in tension in a time-varying manner. Thus, length and tension are unlikely to remain constant when the muscle is active during locomotor activity. Isometric contraction. An isometric contraction of a muscle generates tension without changing length. An example can be found when the muscles of the hand and forearm grip an object. The joints of the hand do not move, but muscles generate sufficient force to prevent the object from being dropped. Isotonic contraction. In isotonic contraction, the tension in the muscle remains constant despite a change in muscle length. This can occur only when a muscle's maximal force of contraction exceeds the total load on the muscle. Concentric contraction. In concentric contraction, muscle tension is sufficient to overcome the load, and the muscle shortens as it contracts. This occurs when the force generated by the muscle exceeds the load opposing its contraction. During a concentric contraction, a muscle is stimulated to contract according to the sliding filament theory. This occurs throughout the length of the muscle, generating a force at the origin and insertion, causing the muscle to shorten and changing the angle of the joint. In relation to the elbow, a concentric contraction of the biceps would cause the arm to bend at the elbow as the hand moved from the leg to the shoulder. A concentric contraction of the triceps would change the angle of the joint in the opposite direction, straightening the arm and moving the hand towards the leg. Eccentric contraction. In eccentric contraction, the tension generated is insufficient to overcome the external load on the muscle and the muscle fibers lengthen as they contract. rather than working to pull a joint in the direction of the muscle contraction. The muscle acts to decelerate the joint at the end of a movement or otherwise control the repositioning of a load. This can occur involuntarily or voluntarily. Over the short term, strength training involving both eccentric and concentric contractions appear to increase muscular strength more than training with concentric contractions alone. However, exercise-induced muscle damage is also greater during lengthening contractions. During an eccentric contraction of the biceps muscle, the elbow starts the movement while bent and then straightens as the hand moves away from the shoulder. During an eccentric contraction of the triceps muscle, the elbow starts the movement straight and then bends as the hand moves towards the shoulder. Desmin, titin, and other Z-line proteins are involved in eccentric contractions, but their mechanism is poorly understood in comparison to cross-bridge cycling in concentric contractions. Though the muscle is doing a negative amount of mechanical work, chemical energy is nevertheless consumed, although less than would be consumed during a concentric contraction of the same force. For example, one expends more energy going up a flight of stairs than going down the same flight. Muscles undergoing heavy eccentric loading suffer greater damage when overloaded as compared to concentric loading. When eccentric contractions are used in weight training, they are normally called negatives. During a concentric contraction, muscle fibers slide across each other, pulling the Z-lines together. During an eccentric contraction, the filaments slide past each other the opposite way. Though the actual movement of the myosin heads during an eccentric contraction is not known, exercise featuring a heavy eccentric load can actually support a greater weight and also results in greater muscular damage and delayed onset muscle soreness 1 to 2 days after training. Exercise that incorporates both eccentric and concentric muscular contractions can produce greater gains in strength than concentric contractions alone. While unaccustomed, heavy eccentric contractions can easily lead to overtraining, moderate training may confer protection against injury. Eccentric contractions in movement. Eccentric contractions normally occur as a braking force in opposition to a concentric contraction to protect joints from damage. During virtually any routine movement, eccentric contractions assist in keeping motion smooth, but can also slow rapid movements such as a punch or throw. Part of training for rapid movements such as pitching during baseball involves reducing eccentric braking, allowing a greater power to be developed throughout the movement. Eccentric contractions are being researched for their ability to speed rehabilitation of weak or injured tendons. Achilles tendonitis and patella tendonitis have been shown to benefit from high-load eccentric contractions.